the question is, so how, if we take a look at the Solow model, if we have one Solow model, we only have one connection between the output level and the growth rate, okay? So if different countries may have different growth rate, G, then the G show up both in the intercept and the slope. So that means we should have a different B0 and different BI. So that means the differences in BI should not be caused by the difference in G. Okay. So the question I raised last class, maybe not very clearly, was that is there any situation that we can justify this equation? So that means you may think about the world through the lens of the Solow model. So if the in which dimension, if the countries are different, then we will have this equation. So I have one example. Some of the students get it exactly right. Of course, you get a full bonus. Some of the students answer following the textbook. The textbook said that in principle, we should have different B1. But for econometric analysis, we cannot have different parameters for both. So we choose the same B1. That's the explanation in textbook. In fact, we have one way to justify the equation. That's my way. Maybe you have another way. So just take a look at this law of motion. So this law of motion is how we derive the regression equation. Okay, the law of motion here. The law of motion here, the equation is not written down in a way exactly the same as the regression equation because you have y star here. Okay, y star is not a variable. Y star is some constant numbers. Okay, for each country. So if you take the y star outside, that should be part of the intercept. Right. So yt is the independent variable. Y star is part of the intercept. So that's the so now we know that if you can find a way to show that different countries may have different y stars, but identical delta, identical g, identical n, and identical alpha, then we can justify this equation. Okay, because y star is part of the intercept. One direct way to justify this is to have a different saving rate for different countries. So take a look at this equation. Saving rate does not show up in anywhere. Okay, saving rate affects the steady state output level, but not anything else. Okay, so that means if a different country have different saving rate, then they will be able to have different intercept, but the same slope. The slope means that if you deviate from the steady state by like 1 point, how many more or less growth rate you would have. If different countries have different depreciation rate, growth rate, or population growth rate, anything related to this part, then those differences will affect both the intercept and the slope. But the saving rate will only affect the slope, only affects the intercept, but not the slope. Okay, so I emphasize this because many of you answer this question verbally without using the model. So, if you use words, it's usually very hard to make the logic very strict. Sometimes you miss something but you didn't realize. So I hope you could think about all these issues or questions in the class through the lens of the models. Okay. But anyway, for those students who tell me that we have to impose the B1 because otherwise it's not doable, I also give you full points. That's the bonus question. Okay, now let's start for today's class. Well, we have a lot to show. Even though the slide is very short, I made it very short in purpose. If we covered everything, that was Asimov's lecture notes for MIT. That will be 200 pages. So it's from chapter 5 to chapter 11 a lot. But I don't think we need to divide them into different chapters, different weeks, because for two reasons. First, so all the models for this week will be using the same tool. Okay, so it's better to make them together. We enjoy the return to scale. And also, I want to leave more time for more advanced content for this class. For example, we may have more time on what people is doing nowadays. Okay, maybe something beyond the textbook in the last 1 or 2 weeks. So that's basically for what we'll be covering this week. So in this week, we will first introduce the mathematical tool of optimal control. I will try to find the simplest way I know to derive all the results we need to know about optimal control. So the most strict proof is very long and tedious. But you still need to know something about the proof. Otherwise, you don't know where it comes from. And it's very easy for you to forget everything afterwards. So honestly speaking, I have learned these materials 4 times. The first time was in my undergrad, second time it was in my master degree, and the third time was in my PhD degree. But for the first 3 times, I didn't really understand the stuff. I do really understand at least enough to give a lecture, only after I learn it when I prepare for the course. Okay, but don't worry about that. Everything is clear here. The logic is clear. So, and then after introducing the tool, okay, let me say one more thing. So, learning many times of this method is also good for me to give lecture, because at least I have the right intuition, right? Even though I don't know the details, I didn't know the details previously. At least I knew the intuition about the content. Once I learned it, once I thought I knew it, I should be really new in this. Okay. So then we will use this tool, optimal control, to have 3 models, to solve the 3 models. The first model is the Ransom model that you already have in the advanced macroeconomic class. I heard from Fred Kwan, who was your lecture last semester. And also, we have a 2-sector AK model, which was an extension to the AK model in Solomon, in 2 different dimensions. And in the last, we will talk about the model for growth based on externalities. So this model is famous. I would say that the author of that model, the one who invented that model, just won the Nobel Prize last year, 2018, Paul Romer. So that's the reason why this type of model is also very famous nowadays. It's hard to say which one is the reason, which one is cause, which one is the loss. Is this guy winning the Nobel Prize because the model is famous, or is the model famous because this guy wins the Nobel Prize? I think maybe the first one is more likely. So he won the Nobel Prize because the model is famous. Okay, let's get into the details. So last class, we have the Solow model. The one of the limitations of the Solow model is that the households are saving mechanically. They don't make the choice optimally. So think about the household in real world. You will choose to consume and save optimally. That is a dynamic choice. So that we need to have a tool for dynamic optimization. Okay. So we also want to make the algebra as simple as possible. Usually, continuous time is hard to understand but easy to write. So that's the reason why people in the growth theory usually choose continuous time. That can save the space for the algebra. Okay, so I particularly choose the version of the optimal control problem that is useful for our class. I leave the central part blank because I would like to use the board. If you cannot see this board, please let me know. Okay? You can raise your hand if you cannot see that clearly. Okay, so in this problem, let me introduce it one by one. So first we have the value function v. Let me follow this order. Okay. First we have the state variable x. You can think about x as a capital, the knowledge, or anything you can accumulate that evolves across time. You cannot change this variable, or you cannot. This variable cannot jump. So suppose you have $1,000, 1,000 Hong Kong dollars in your pockets. So you cannot have million in the next minute. Right? To accumulate something little bit. So that's the state variable x. And we have another variable y, which is the control. So this is something you can choose flexible. For example, you can choose to eat, or you can choose to pay $200 to go to a restaurant, or pay $500 to go to a good restaurant. So you can choose these numbers freely. That's y. Okay. And the one which do the optimizer are choosing these two paths, xt and yt. So these are dynamic paths. We define these values for these two variables across time. So they choose the path of these two variables to maximize the right-hand side. The little f is the objective function for the very short period of time. So it's the happiness that you enjoy in 1 minute, okay, for example. So we can call this the instant value. So this value depends on x and y. So for example, if you choose to have some consumption c, okay, then c will be the control variable, and you will enjoy some utility from consumption. That is y. And also sometimes x enter utility. Some people just like money. Okay, just like some officers who are corrupted. The corrupted officers, they just collect a lot of cash from the positions, and they hide the cash under the mattress, under the bed, in the bedroom. Each time when they went to sleep, they open it and have a look. They feel very happy. So it's possible that sometimes the state variable x also enters the utility. So that's the reason why we have x here. It also depends on time. That's the reason we have time. The notation SUP is trim. So it's a generalization of maximum. So usually we have a max here for the simple case. Here it's better to have SUP because it covers a case in which you may have some bounded upper bound. I can give you one example. So think about the set of negative real numbers. Okay, the set of negative real numbers have exact upper bound 0. All these numbers are smaller than 0, but none of these numbers can be exactly equal to 0. So in this case, the supreme of this set of negative real numbers will be 0, but there is no element in the set that is exactly equal to 0. Okay, so if you think it's too complex, you can just treat the supreme as a max. Okay, for simplicity. In this problem, the left-hand side we have the value function. this is the evaluation of all the values you can obtain from x and y from one point of time. For example, here you are evaluating the value at period t0. Okay, at this period, the state is xt0. That is what you have, how much money you have, and the t tells you the time. So given the time and the money you have, you know your present value of the discounted future utility, something like that. Okay. So and also there are terminal conditions here. We need to have a starting point, xt0. You need to know where you start from, how much money you have now in order to know your future value. Okay. And also you have to have some constraints on the terminal condition, which is the limit for xt when t goes to infinity. For example, you try to make a plan for your whole life and your next generation and next generations. You want to choose some way to do investment. Okay, and in this situation, there must be some constraints on your choice. For example, you can have like positive numbers of stock or savings in the bank, but you cannot have negative or too much negative. For example, if you continue borrowing money and you let the debt accumulate across time and let the debt go to infinity, if that happens, of course you can have a lot of consumption during your life, but you will be debt with a lot of debt in your balance sheet. So we don't want that to happen, because if that happens, then you have no way to restrict the one who is doing the optimization. The optimizer can always choose to consume more and save less or borrow more, and there will be no upper bound for your lifetime utility if you can continue borrowing. Okay? So that's the reason why we impose some restrictions here. Your state variable has to be at least something for you. For example, when you your debt, you have to have at least 0 wealth. I just give you one example. Okay. So based on that, when you do optimization across your whole life, you cannot consume infinite amount of goods, because you have to have 0 wealth in the end. So that's the basic idea of this optimization problem. Now we try to figure out how to have a simple way to solve this problem. Let me try to derive step by step. So first, let's use a notation, x hat and y hat, to denote the optimal path. The optimal path is the path when you choose it, you obtain the optimal value, the supreme value. I just mentioned that you may not be able to achieve this one. This one may only show up in the limit, but not in reality. But here, we assume that there is a path which is optimal, and in this path you can get the best value you have. Okay. So if this one is possible, we assume this. If this is possible, then we have the first lemma, the principle of optimality. So this formula tells you that if you are on the optimal path, then your current value will be equal to your future value divided into 2 parts. The first part is the accumulated value starting from period t0 to t1. Okay, and the second part is the value starting from period t1. Well, this one may seem to be obvious, but it is not. The reason is that we know that this value, let me write it down. this one can be divided into two parts. Okay, divided into two parts. Now the question is whether the second part is identical to this one. So if we want the second part to be identical to this one, it must be the situation that the optimal path x hat and y hat starting from period 0 is also the optimal path when you start from period t1. Okay, so this one equal to this one. According to definition, the x hat and the y hat has to be the optimal path starting from t1. Okay. So why can that be true? So we can prove this argument by contradiction. Suppose you have choose this optimal path starting from t0, and from the t1, you suddenly find that the original path you chose is no longer the optimal one anymore because the situation has changed. You are facing different circumstances. If that happens, it must be possible for you to change the path of x hat and y hat beyond the period of t1 to improve your value. So in that situation, you can have a better value of this part to get closer to the second term here. If that happens, now we can move back to period t0 to think about what you do. You change your plan for the period after t1. If you take a look at your whole plan starting from period t0 and connect the first part and the second part, you also change your whole plan, right? So if by changing the second part of your plan, you can improve the second part of the value, it must be the situation that you also improve the whole value. Because the first part is not changed, the second part is improved. And that, if that is true, then we get some contradiction that the x hat and y hat is the optimal plan starting from t0. Okay. So that means the assumption we imposed is not true. In other words, this plan is also optimal if you start from t1. So that's the reason why we have this formula, the principle of optimality. So in short, this one can be summarized in one sentence. In the optimal control problem, if you set up a plan in the very beginning of the time, if the plan is optimal, then the plan will always be optimal, regardless of what happens later on. Okay, that is the optimal plan. And sometimes we call this the time consistent plan. So you will not regret later on once you have the initial plan. And also, this is like the situation when you make a commitment. You make you make a commitment to go to the gym for your whole semester, and after 1 week, you still think your original gym is optimal if you know yourself sufficiently. Of course, in the real world, people do regret, right? Partly because people do not fully understand themselves. Maybe they try to go to the gym and they find it's too tough for them, and then they change their mind. That happens because people do not understand the situation sometimes. But in our mathematical problem, we assume that everything is perfect foresight. You know everything about the environment, and you do the optimization. You should be able to commit and have no regret. Okay. That's the lemma here. This lemma is important because we can use it to derive a lot of things later on. Okay, so then we move to another important theory, which is the HJE equation. Hamilton Jacobi-Bellman equation. I never remember this name. Just remember HJB. HJB. So it's like the optimality condition in some problems. We can obtain this HJB equation directly from the principle of optimality. The idea is very simple. The principle of optimality is not very easy to use because we have some integral here. So we usually hate the integral in algebra. We want to eliminate this integral. So the first step, we replace T1 with T in this formula. Okay, so this is directly from the level of principle of optimality. And then we try to take derivative with respect to T on both the left-hand side and the right-hand side. For the left-hand side, it becomes 0 because the left-hand side does not depend on T. For the right-hand side, the first term is the integral. If you take derivative, then it becomes the function inside, evaluated at pure T. So it becomes ft x hat y hat. And for the last term, it has two arguments related to T. Okay. So for the first one, you have this partial derivative. For the second one, you have to use the chain rule. The first to take partial derivative with respect to x, and then take derivative of x with respect to t. We know that here, x to t, derivative to t is g. So that's the reason why we have g here. So that means, in short, the HJB equation is just the first order differential version of the principle of optimality. Okay. Now here comes the most important method we need to know. So this is the tool we're going to use for the whole week. So this is the infinite horizon maximum principle. Suppose we have the optimal path x hat and y hat. These optimal paths must satisfy the following conditions. This is a necessary condition. Okay. So once you apply all these conditions, you find all possible candidate solutions for x hat and y hat. If you get one unique solution, congratulations. You may have multiple, but that's fine. You can deal with that in more detail later on. But usually you will get a unique solution through this method. Well, there are a lot of equations here. Three are a lot. Maybe it's not so easy to keep on remember these things in your whole life. So that's the reason why I try to show you an easier way to prove these conditions. We don't have to prove the last line. This is just given by the problem. The second to the last line is just law of motion. Take a look at the Hamiltonian function. If you take a derivative with respect to lambda, then you get g function. Okay. So that means h take derivative with respect to lambda is just a g, and g is given by the law of motion here. So that's the reason why you have the third equation. It's so obvious. Now the problem is how to get the first two. Also not too hard. Remember we have the HJB equation. HJB equation here. Okay. This one must be true if the path is optimal. So now we can play with this equation. Let's try to take derivative with respect to yt. Okay. So if you do that, then this one becomes f to the derivative of, let me write it down. So 87. You take derivative with respect to y, so this one becomes fy, okay? The second one has nothing to do with y. So this one becomes 0. This one, nothing to do with y. And this one, something to do with y. So we have this one's equal to 0. That's the first order condition. And what's this? I will talk about that later on. Let's move on. So we can also take first order derivative with respect to x of this equation. Then you have fx, first term. The second term will be you take derivative twice. There may be a typo here. So twice, and then you plus this term. This becomes twice, okay? Twice.